Okay, good morning, everybody. Welcome today. I guess you saw the results of our election yesterday. We were a little bit shocked, to say the least. But we woke up for another day, so that's a good sign. Um, so, yesterday we talked about some of the structural and functional techniques that are used for brain imaging, and today we're going to get into magnetic resonance imaging. So this is the technique that I'm most familiar with, and we're going to go through a lot of detail about how it works and what people use it for. This sometimes will get a little bit technical today, so if there's anything that you don't understand or if anything's not clear, just raise your hand, let me know, and we can go through the concept again. So Felix Bloch and Edward Purcell were the first to use NMR techniques in 1946. They were awarded Nobel Prizes for physics in 1952 for the discovery of NMR, and NMR is nuclear magnetic resonance. They found that nuclei placed in a magnetic field absorbed energy in the RF is radio frequency range of the electromagnetic spectrum, and re-emitted this energy when they return to their relaxed state. So you can put in energy into atoms, and they found that you can also receive energy back from them. So this was sort of the birth of the idea of nuclear magnetic resonance. I'll explain more about it. This man, Raymond de Modeun, was the first to demonstrate that NMR tissue had that different tissues had different properties if you place them in a magnetic field and use nuclear magnetic resonance with them. And he did this by demonstrating differences between normal tissues and tumor samples in the late 60s and 1970s. So these were just some of the early people that used this technique, these techniques, and helped to develop them. In March of 1973, Paul Lauterbur, he was one of the pioneers of using MRI to do imaging. So he was the first to make an image using nuclear magnetic resonance. He was awarded a Nobel Prize in 2003 for this discovery, along with Peter Mansfield. So there are several uses of magnetic resonance that have developed since the first discovery of it. One of them is nuclear magnetic resonance spectroscopy, and you can use this to determine the chemical composition of materials. So if you're a chemist, you may use this technique a lot. We'll talk about the principles of it and when we talk about MRI, and then later you can sort of see how NMR works. We'll talk about that a little bit more. I just want to go through the basic things that you can use magnetic resonance for. Magnetic resonance can also, as we know, be used for high resolution anatomical imaging. And the beauty of this technique is that the method itself provides sort of an endogenous way to contrast different tissues. So we can do this without injecting any kind of dye or anything, radiation or anything harmful into the body. Since the inception of functional MRI has began, and that came about in the 1990s, and this technique has just really skyrocketed as a way to study the brain. So it started very slow, and now if you look today and do a search fMRI on Google, you'll get just an incredible amount of hits for it. So it's become quite a popular technique. You can also use MR for diffusion tensor imaging, which we're going to talk about in a lecture later. And as I mentioned, you use use the diffusion of water and rely on this technique to make images of white matter tracks, and you can look at the connectivity between different gray matter areas and between different cells in the brain using this technique. So I'm going to talk a little bit about the MRI environment. This is an MRI machine here, and this is what they pretty typically look like. There is a large round circle in the middle, and that's called the bore of the magnet. The magnetic field is around, contained within this, well, it's generated within this loop around. And so inside there is where the magnetic field is the highest. And it's best, as we will see later, if this field is uniform. So that's why they have the circular technique. Nowadays, a lot of people are claustrophobic and have trouble going into this machine. And if you're very large, you might have trouble fitting in there as well. The smaller the bore is, the more easy it is to maintain a uniform field. So that's why they don't make magnetic MRI machines that are huge. They have also started doing this MRI between two plates, and they use that often for clinical uses. The problem with that for research is that, again, it's really hard to keep a uniform field within two plates. So we don't use that much for research, which limits the types of participants that we can use. Because, of course, like I mentioned, if they're claustrophobic or have any fears about confined spaces, it's difficult to image someone in that. So for clinical uses with the two, it's called open field MRI. It's good enough to see problems in tissues and things like that. So it's an option for clinical uses. So now we're going to go into a little bit about how MRI works and the basic principles of it. And I try to divide this down into some different points so we can tease apart these and try to understand this step by step. So we're first going to talk about magnetism and nuclear spins and precession, which is the background of how and why actually magnetic resonance works. We're going to talk about the RF pulse and the free induction decay. We're going to talk about some of the contrast parameters that are used in MRI, which are T1, T2, and T2 star. And then we're going to talk about how these contrast parameters are used to be able to see different tissues in the image. Okay, I don't know what your physics backgrounds are, but just a little bit about electricity and magnetism. The electricity and magnetism travel together in perpendicularly to each other. So if you have an electric field, you're also generating a magnetic field, and vice versa. So the top right shows you how this works. So if you have a current running through a wire, you'll have a magnetic field going around it perpendicularly. Down at the bottom shows a magnet, and if you have a magnet with a north and a south pole, these are how the magnetic loops work around these magnets. So you can see here that a field is generated around the magnet with the poles. Like I mentioned before, nuclear magnetism was discovered by Felix Bloch in 1952, and he won a Nobel Prize for this. And what he proposed was that all nuclei with an odd atomic weight have a property called spin. So an odd atomic weight is, of course, there's many elements that have this property. And in MR, we're generally interested in the hydrogen nucleus, or a proton. So we're looking at hydrogen atoms with a positive charge. These protons have an angular momentum and a magnetic moment. And P is dependent on the number of protons and neutrons in the nucleus, P being the angular momentum. So let's look at the hydrogen atom. Protium is the hydrogen atom with a mass of 1. Deuterium, I'm not sure if I'm saying that correctly, has an atomic mass of 2, and tritium has an atomic mass of 3. So these are just different ways the hydrogen atom can exist. I'm not a chemist or a physicist. So these are just my rough understandings of it. So if anybody has anything to add or has a better understanding of these things, just raise your hand and feel free to contribute. But the most common hydrogen isotope is protium, and its abundance is more than 99.98% of hydrogen. So the nucleus of this isotope contains only a single proton, and the cation of this proton, of this protium, is called a proton, and which is denoted by H+. Okay, so protons are present in a large amount of the fat and water of the human body, and these hydrogen nuclei have a nuclear magnetic signal and act like tiny tops that wobble as they spin. So they're randomly oriented and they spin in a field. Let me see if I have. Yes. Okay. So the hydrogen atom, or the proton, acts like a small magnet. So they point a direction because they have a charge on them. And in the absence of any external magnetic fields, they're basically randomly distributed. So you can see here how the atom spins and has a pole, a north and a south pole, like a magnet. And in the absence of any field, they're all randomly distributed in the ways that they point and spin. Okay, so now we're going to add an external magnetic field, and we're going to call this field B0. And this is a constant in the strength of the magnetic external field. And this magnetism is measured in Teslas. 1 Tesla is equal to 10,000 Gauss, and a half of Gauss is what the magnetic field is at the Earth's surface. So if you would measure the magnetic field at the Earth's surface, it's a half a Gauss. So you can see that 10,000 Gauss, or 1 Tesla, is quite a big field strength. So as I mentioned, magnetism is measured in Tesla and Gauss. And here are some other facts for you. The Earth's magnetic field is, like I said, a half a Gauss. A refrigerator magnet, or one that you might stick to your refrigerator, is about 50 Gauss. And if you start talking about MRI machines, 3 Tesla is the typical field strength that we use for our fMRI experiments, and these are equivalent to 3 Tesla or 30,000 Gauss. At the University of Pittsburgh, we now have a machine that is 7 Tesla, so this is again 70,000 Gauss, and it's quite a big field strength. We have to have special considerations when you put somebody in a field like this, because, as I mentioned, magnetic and electrical fields travel together. So when we put somebody into a 7 Tesla magnet, you basically put them on a table and slide them in. They tend to get dizziness because this high magnetic field is causing their neurons to have different properties than they would in the absence of this field. So sometimes they'll feel nauseous and dizzy going into the field. So, and to try to alleviate this, we try to slide them in as slowly as possible rather than just slide them in quickly to the magnet. But some people can't tolerate this feeling, so you have to think about special considerations when you use a magnetic field that high. So the magnet itself is the most expensive part of the MR scanning system. And there are actually 3 magnetic fields that are used in an MRI machine. The static field, which I mentioned, is B0, and that is the one that I referred to as at our machine is equivalent to 3 Tesla. So this is a permanent magnet. The magnet is never shut off once it's on. We'll talk a little bit later about how they keep this magnetic field going. And I think it's a very clever technique. They use superconductivity in a super cold wire to keep this going. But you have to remember when you're around this magnet that the field can never be turned off. So this is especially important to think about safety. You don't want people wandering in there with magnets. It was interesting. We actually had A few weeks ago, we were up scanning a patient at night, and the janitor came in with a big mop and bucket and said, "Is it okay if I go into this room?" So we were quite appalled because the people who are come in contact with in this and are in this environment are supposed to be trained to know that they can't go in there. And in fact, there's big signs everywhere saying, "Do not enter this room unless you have been screened." So it's always a bit surprising how people get past that and don't read the signs. But safety is a big issue. People have been killed with these high magnetic fields because of the pooling of the magnet. So let's see. So it's superconductive and it's resisted. So resistive. It needs electricity to generate the field, and this is again done by the fact that magnetic fields and electrical fields travel together. So another field that we use in this MRI machine is a radio frequency, or referred to as an RF field, or B1, and we use gradient magnetic fields, and we'll see later how these gradient fields are used to actually create the image of the MRI. So there's two important features of the magnet: the homogeneity, which I mentioned, which is having a uniform magnetic field within this magnetic bore, and stability. So we want this magnet to remain stable over time. Every morning before scans are done, somebody comes in and checks the magnet for its stability. So if you have a magnet that's changing properties over time and you want to do imaging on different days, this would be a problem because characteristics of your image might change if that field doesn't remain stable. So we're going to talk a little bit about the magnetic susceptibility of different substances. So there are three different properties in terms of magnetics that a substance can have. It can be diamagnetic, which means it has no unpaired orbital electrons. So oxyhemoglobin, water, and most substances in nature are diamagnetic, and they're weakly affected by an external field. So we have paramagnetic, which means they have unpaired orbital electrons. So they become magnetized by an external field, but they don't retain this magnetism in the absence of a field. So this would be like our hydrogen atom that we were talking about. If you put it in a field, it'll point to a certain direction because it has an unpaired electron. And then there's ferromagnetic, which means something that is permanently magnetized by an external field. So when you think of an actual metal magnet, this is something that's ferromagnetic. So you take it out of a magnetic field, it still retains its magnetic properties. You put it next to the refrigerator, it's still going to immediately be attracted to it. So that is something that is ferromagnetic. Okay, let's talk again about hydrogen. So remember, I told you in the absence of a magnetic field, these hydrogen atoms have a spin and they have a north and a south pole like a magnet. And they just randomly face any directions in the absence of this field. But if we put them into a magnetic field, then they start to line up because of this because of this charge that they have on the atom. So you can see here on the right, that's them in the field, and they're lining up into the field of the magnet. So they can either face towards the magnet or away from the magnet. So you see the arrows pointing to the right and some to the left. Most, however, point in the field of the magnet to the right. Okay, so we know now that we put a magnet in there and our hydrogen atoms are spinning away in the B0 field, either pointing parallel, which was pointing to the right, or anti-parallel to the field in the orientation. And they actually are at a slight angle. Well, I guess it's a pretty big angle. But they're at an angle in this field, and they're trying to align with the B0 field, and it creates a torque, and they're spinning, and it's similar to the motion of a gyroscope. Do you guys know what a gyroscope looks like? You spin it and it sort of wobbles around like a top. And so that's what our hydrogen ions or atoms are doing in the field. And the frequency at which they're spinning is called the resonant frequency or the Lamar frequency. So the equation here, the frequency at which our atoms are spinning are equal to what's called a gyromagnetic ratio, and this is a tissue or a molecular dependent property. So if you would have hydrogen, our gyromagnetic ratio is equal to 42.6 megahertz per Tesla. If you would have a nitrogen atom, it might be a different number. So it's dependent on the type of atom that we're looking at. So the frequency at which our atoms are spinning is equal to the gyromagnetic ratio times the strength of the field. So at 3 Tesla, that would be 42.6 times 3, and that would be what's equal to of our frequency of the atoms they're spinning in. Okay, does that make sense? Is everybody following? Okay. Okay, so we can think of the effect of all the protons as a net magnetization. So they're all lined up in this field. They have a magnetization in the direction of the field, and in this case, we're calling that MZ. That's the field in the Z direction. So if you think about that MRI machine, the Z direction would be into the magnet. So that sort of the field that's created around the loop, and I think I have a picture, yes. So that would be the Z direction that they're all lined up into. And that's the person, of course, laying in an MRI machine. Okay, so they're all lined up in this direction, spinning away. Okay, so if we all have a good concept of what's going on there, all our atoms lined up in the field spinning, then we're going to talk about the RF pulse. So we're ready to move on to the RF pulse. Does anybody have any questions? Okay. All right, so the next thing we're going to do is add this radio frequency pulse. And the radio frequency part of the electromagnetic spectrum in which electromagnetic fields can be generated by alternating current feed to an antenna or current fed to an antenna. So the RF pulses are commonly in the range of 1 to 100 megahertz, and they can be a source of potential heating of tissues in foreign bodies. So this is another safety concern to think of when a person is in the magnet. We're going to add this RF energy to our tissue, and if they do have metal or things in the body, then this can cause it to heat up. So we'll talk about that a little more when we talk about safety. And this is a principle of concern for MRI, as I mentioned, because of the absorption of this energy into the material. Okay, so the radio frequency pulse is going to be applied to the protons at their resonant frequency. So remember, I told you the resonant frequency was dependent on the gyromagnetic ratio times the strength of the field. So this is their natural frequency at which they're spinning. And we're going to apply the RF pulse at this frequency. And you can also think of resonant frequency if you think of a child on a swing, okay? So they're swinging back and forth, and the frequency that they're spinning at is, we'll call that their resonant frequency. So if we would come and we would push the child on the swing out of rhythm with their frequency, what's going to happen is that the swing's going to go crazy, and they're not going to go anywhere. But if we push them at the resonant frequency, so when the child comes back and we pushed at the frequency that they're already going, that's what's putting more energy into them swinging back and forth. So if you think of a resonant frequency, it's basically the natural frequency that something is going or spinning at. So we're going to apply the RF pulse at this resonant frequency, and it's going to cause all our hydrogen atoms that are spinning in the field to tip. And let's see. Okay, so here's what it's going to do. So at the top left here, they're all spinning around at the resonant frequency, And we're going to add an RF pulse, and then you can see there right underneath, they're going to tip all 90 degrees. And as they're doing this, they're continuing to spin. So you can see on the left there, those are representing each of all of the atoms as they're spinning. On the right there, this is a net magnetization. So the net magnetization is in the Z direction. Once we tip it, we're tipping it over into the XY plane. So we're knocking them down into the transverse plane. So what do they do after they get knocked down? Well, they're going to try to line back up to the magnetic field again, right? They want to be back to their lowest energy state in the B0 field. And as they do so, they emit energy. So as the magnetic flux changes in an enclosed loop, a current's produced, and we can measure this with the RF coil. So there's two things that's going to happen after we tip them over. There's one is they're trying to get back into this magnetic field that they line up into. Another thing is that while they spin, they're initially all in phase together. Phase meaning at the rate of which they're spinning. And they're going to, so they're all locked together, phase locked. And as they start spinning in after they've been tipped, these phases are going to start to distribute and not be all lined up again. So that'll be more important later when we talk about the T1, the longitudinal relaxation, and the T2, the transverse relaxation. Okay, so what is the free induction decay? That is the energy signal that we measure as these protons are trying to get back to their lowest energy state. So this is the actual signal that we measure that's going to create our image. And again, this is called the free induction decay, and it's an oscillating exponential decay. So you can see the function for it here. And that's going to be important when we go to recreate our images, because remember that Fourier transform that we talked about yesterday that oscillates as a function of sine and cosines, that's what our signal is going to be composed of. It's going to be a spatial oscillation, and then we're going to use that fact to reconstruct our data into an image. Are you guys all following okay? I know it's a little tricky. Just want to get you the basic idea of what's going on here. Okay, so number one, all our hydrogen atoms were aligned in our field. Number two, we applied this RF pulse to tip them all 90 degrees. And number three, they're going to start emitting energy as they try to get back into their aligned state. And as they do that, they're emitting this signal, which we're calling the free induction decay. Okay? Everybody's good so far? Okay, so now we're going to talk about these T1, T2, and T2 star parameters. Okay, T1 is called the longitudinal relaxation time, and it's also been called the spin lattice relaxation. So again, this is our atoms trying to return to the state of alignment of the magnetic field of the B0 axis. This is a tissue-dependent property, and this works out well for us because this property is going to allow us to see how different tissues look, because they're all trying to get back into this alignment, but they're doing so at different rates in different tissues. Okay, the T2 is the transverse relaxation, as I mentioned. It's also called the spin-spin relaxation. And this is the loss of phase coherence between protons as they decay back into the field. So if you can see here on the left of the XYZ axis, when you first tip them, they're all together as they tip down. And as they start to go back into the field, they're also losing phase coherence with each other. So you can see after a little bit of time, instead of having one net arrow pointing this way, now we have those three little arrows because they're all starting to separate in phase. And after more time, you can see that the phase of these atoms are all now pointing in different directions. So initially we tipped them and they were all aligned together, and then they start to spin out of phase with each other. This net decrease in the net magnetization in the XY plane is because of the interactions between protons, and because of the fact that we never have a completely homogeneous magnetic field. And the homogeneous field, of course, is the distribution of the magnetic field. Remember, I said we want to keep that as uniform as we can. T2 is also a tissue-dependent property. Okay, so I'm going to make the distinction between T2 and T2 star. T2, again, is the transverse relaxation in a perfect magnetic field. In a perfect magnetic field, the T2 relaxation is depending completely on the tissue type. However, the field's not going to be perfect. So T2 star is the loss of the phase coherence due to the inhomogeneous magnetic field. So T2 is actually equal to, we'll call it T2 prime, that's our perfect transverse relaxation, and T2 star, which is the relaxation due to the fact that our field is not homogeneous. So T2 is actually equal to the sum of the perfect transverse relaxation in a perfect field plus the relaxation caused by the inhomogeneities of the field. So this T2 star causes a faster decay in the signal, and while it's inconvenient for anatomical imaging, we'll see later that this T2 star is actually what we used when we look at functional magnetic resonance imaging. So here is, you saw this in the other figure, that as those arrows started to separate in the XY plane, okay, so these are the factors affecting the transverse magnetization, as I said. So T2, a perfect T2, is the dotted line up top. So this is the rate as which we're losing that phase coherence or the XY relaxation, and it's tissue dependent. However, because we have these field inhomogeneities, it's decaying at a faster rate. So you can see the line caused by the T2 star there. So our T2 is going to be actually somewhere in the middle of that. Okay, so we're going to talk about why different tissues have different T1 and different T2 properties. So T2 in solids, the molecules are closer together. So this results in a faster dephasing of the atoms after you tip them, because they're having interactions from different different atoms that are nearby. So the closer together they are, the more dephasing or the faster dephasing they're going to have, because they're influenced by the things around them. T1 depends on the physical state of the tissues as well. The protons can give off or absorb energy from their surrounding lattice. So let's see. So T1 has a faster decay in tissues that are more viscous, or so tissues that have more loose atoms basically have a faster T1. So if they're not packed together as tightly, they can go back into that magnetic field more quickly. Does that make sense? So they're trying to line back in the field, and if they're not packed in a tight lattice, they do it much more quickly than something that would be atoms that are packed together. Okay, does that make sense for these T1 and T2s? You guys following that they're tissue-dependent properties? So here's some of the properties that you can see in this table here, and the values of T1 and T2 for each. So you can see that fat it takes 260 milliseconds after you tip these for the tissue to come back into the field. And in terms of dephasing, it has a mid-range value of the dephasing, because fat isn't a bony structure that's packed tight, but the atoms are closer in fat than they would be in another material. Okay, so one thing we can do is change the times between the RF pulses, and this is called the TR, the time of repetition. So this is the time between 2 RF pulses. And TR is pretty important when it comes to fMRI. So it's also important in structural, but I tend to think of it as more of a fMRI parameter that we continually try to make the machines go faster and faster so we can collect more functional data. And then the time when the FID, or that's the free induction decay signal, is measured is called the TE. So that's the echo time. That's what when we send the pulse, and when we listen back to the pulse, that's our echo time. That's the TE. So that's the amount of time that we wait to allow both dephasing and longitudinal relaxation before we sample the tissue. And you're going to see how these different TR and TEs work to make the contrast. Okay, so let's look at the contrast effects of T1 first. Okay, so you see we have a slice of tissue, we send the RF pulse, and now we're waiting to take our echo. So what's going on during this time is that the tissues are trying to line back up in that field, right? They're trying to get back into alignment with the magnetic field, but they're doing so at different rates. So you can see here there's tissue A and tissue B, and tissue A is lining up into the field faster than tissue B here. So let me go over here. I guess you guys can probably see that without me pointing it out, right? So tissue A is getting quickly back into the field, and I'm sorry, tissue B is going back more quickly in this case than tissue A. Do you see that? So the one is going quickly, the other is going more slowly into the field. So which tissue has the longer TR in this case? Yes, tissue A. And so now what we're going to do is we're going to measure listen to our echo. And if we do so, you see at this first TR, we have a big difference between these two tissues, right? But if we wait till the TR2, these tissues are nearly identical. So in this case, which TR do you think would give a better contrast between the tissues? It would be the first TR. Okay, so if we listen to our echo at the first TR, we have this differentiation of the two tissues because one is relaxing more into the plane more quickly than the other. Okay, so here's an example. This is called a T1 contrasted image. And in a T1 contrasted image, the CSF is generally black. And you can see here that the white matter and the gray matter are going back into the T1 plane, into the longitudinal plane more quickly than the CSF. And so when we measure at a shorter time, we're going to be able to see the contrast between the CSF and the white and the gray matter better than if we wait a longer time. So say if we measure right here and listen here, we have this big contrast effect between these two types of tissues. So to do a T1 contrast, we would want to measure at a short TE. So we'd want to send our TR pulse, and we'd want to listen pretty quickly so that we can see this contrast before all the tissue atoms all line up again into the plane. Does that make sense? Okay, on the other hand, we could T2 contrast, and T2, again, is the property of dephasing in the XY plane after we tip. So in this case, we have two different tissue types, and they're decaying into the dephasing. And in this case, which tissue has the longer T2? Do you think it's the... Yes, tissue A is taking a longer time to dephase. So if we would listen to immediately, we would see that there's not much difference between the two tissues. But if we wait a longer time, we get a better contrast between tissue A and tissue B if we're looking at a T2 contrasting. Okay, so here's an example. We have to do a T2 contrast, you would have a longer TR and you would have a longer echo time. So you would wait a little bit longer to measure the difference between the tissues. And in a T2 contrast, the CFS comes out white now instead of black, and the rest of the image comes out darker. Okay, so here's another example of T1 weighting, and I think this is probably a better picture on the right there of showing a T1 weighted image. So the CSF in this case is black, and the bone around the skull is white. So again, we would wait, we would send the signal, and we would read it pretty quickly. So you can see there that there's a big contrast between the tissue with the short T1 and the tissue with the longer T1. And again, here with the T2 weighting, we would send our pulse, and then we would wait before we take the sample, a longer TE time, so that we would allow for this dephasing to take place. And again, you can see a T2 weighted image here. And if we wait here to listen to where there's a good separation or contrast between the tissues, then we can see more of a difference between the tissue types on our image. Does anybody have any questions? Okay, there's also something called a proton density weighted image, which you would do a longer TR and a shorter TE. So I'm not going to explain too much about this, but the contrast in this case is mainly due to the differences in the number of protons in the tissue rather than the difference in the time and the relaxation and the dephasing of the properties. Okay, so does anybody have any questions about that before we go on to our next topics? I know we went through that pretty quickly. Okay, so we're going to go on and we're going to talk about spin echo pulses. We're going to talk about distinguishing spatial information. So we know that we can send the pulse and read it and see the different tissue types. But how do we actually know where these differences are? So how do we get the 2- and 3-dimensional images in here? We're going to talk about pulse sequences and other pulse sequences. Then we're going to talk about recording the signal and instrumentation. Okay, so a pulse sequence is a set of RF pulses applied to produce specific results. And remember, the pulse sequence is going to depend on the TR when we send our signal and how often we send our signal. And the TE is going to be, again, when we listen to our signal. So we send the pulse, and then we wait for this free induction decay comes back, and that's what we measure. So spin echo is actually a very clever technique that's used in anatomical imaging, and it involves refocusing the protons while they're decaying in the XY plane to get a better signal or to get a peak in the signal. And this spin echo pulse sequence is used to eliminate the dephasing effects caused by T2 star. So it's going to get rid of these T2 star effects, which are again due to the inhomogeneities in the field. And because of this, we can use this spin echo pulse sequence to actually measure the T2 of tissues, since T2 star equals T2 in the perfect field, right? There's no extraneous effects of the inhomogeneities in the field. Okay, so spin echo is actually a really clever technique. And you can see at the top, this is showing when the pulses are applied. So the first thing we do is we apply, or we have our protons lined in the field. We're going to apply the 90-degree pulse, which is going to tip them into the XY plane. And this T2 effect leads to this dephasing. However, at a time of tau shown here, as these are spinning in the plane, we're going to apply a 180-degree pulse. And what's going to happen here is that they're going to keep spinning, but they're not going to change directions of their spin. So since we flipped it over, before they were diverging, and when we flip it now, they're going to, all our proton phases are going to converge and go back to a single point. And I'm going to show you how this works a little bit more. But so our signal is going to drop because of the phase going out of sync with each other. But we're going to apply this pulse, and then the signal is going to reach its strength again because all the protons are going to get back into phase again. Okay, so this is an analogy people like to use. It's the runner analogy. So this is basically what happens. So we have runners starting at the same point, like protons starting to dephase after the 90-degree pulse. And they're all running at different speeds. So like T2 star effects, they are dephasing because they're going at different rates. However, if we have them all turn 180 degrees, but can keep running at the same rate that they've been running, they're all going to reach the starting point at the same time again. Did you guys see how that happens? So again, they're all reach the starting point at the same time as long as they continue to run at the same speed that they ran before. And this is, again, how everything's going to converge and make our maximum signal again. So isn't that pretty clever? Whoever thought of that? Okay, I actually do have a video, but I don't think I need the sound. Let's see. Whoop. Is it uninterneted again? It's just another driving this point home video. Okay, so this guy's going to show an example of how this works. Okay. So here we go. We apply the pulse. So that is spin echo. So that is how they get a maximum signal, and they get rid of that T2 star effect of the field inhomogeneities. So they don't get rid of the T2 effect because T2 is a tissue-dependent effect of different properties, but it just gets rid of that dephasing caused by the imperfect field. Okay, so now we're going to talk about how do we distinguish spatial information in our image. So that's pretty important, right? Because if we couldn't do that, then we wouldn't get our 2 and 3-dimensional image. Okay, so far the signal we've discussed is just the sum of the individual signals from each individual proton. So what I'm going to ask again at this point is, what are we using to create the image? And that's basically what we're measuring. This free induction decay signal is what we're going to use to make our image. Okay, so remember that our omega, the frequency, is going to equal the gyromagnetic ratio times the field strength, where B is the magnetic field strength, and gamma is a constant, and it's used to tip the resonant frequency at the strength omega. But by slightly changing B, we can alter the resonant frequency or the amount of energy needed to tip the protons. Okay, so here's what we're going to do. Okay, in a given area of tissue, each region experiences its own little magnetic field. Gradients or differences in this magnetic field, variations in this field, can allow us to define a positional location of each of these protons. So there are 3 coils in the magnet, and these are used, one X, one Y, one Z, and these are used turned on and off as we image, and these are used to define our spatial locations. And interestingly, if you've ever had an MRI, you know that they're very noisy. We have to give our people earplugs so they don't damage their ears when they're getting their scan. And this noise is actually due to these spatial gradient magnetic fields switching very quickly, because they need to switch quickly in order for us to get this spatial information. Okay, so the gradient fields are needed for imaging. So we have our big B0 field, and then we're going to have these gradient fields around to measure the locations. So say we wanted to select a slice of tissue here. So here's what we would do. We would add a linear magnetic gradient, GZ, along the Z-axis, so that our field at BZ is going to equal B0 plus Z, the location, GZ. So our field is going to depend on where we're at in the Z direction. And by doing so, we can change the resonant frequency of these protons at different slices in the tissue. So instead of sending something at exactly each resonant frequency at the same place, we would slightly alter the field so that we could get the spatial information in the Z direction. Does that make sense? Okay, so we would apply the RF pulse at a frequency, omega S, and a bandwidth, and then we would do a typical shape of slice selection. So this is the pulse we do to define the space, the RF amplitude there. And only the protons in this specific slice area are going to tip because of this pulse, because they have a specific omega now, a specific resonant frequency that's going to differ from the other slices because of this variation in the field. Okay, so say we would want to take a coronal slice. We would apply this varying field in the Y direction. Okay, this is this way. Again, coronal meaning you're going to cut the face off here. If you want to go in the axial direction, you can apply this in the Z direction. And this is the typical way that we scan in the axial direction for our participants. Or if you wanted to do it in the sagittal direction, remember the sagittal makes the symmetry. If you cut slice right down the middle, then you would apply this selective RF pulse in the X direction. Okay, so now we see how we do the Z direction by making our slice unique to its resonant frequency. We can also vary the information in the XY plane to determine the spatial location of the recorded signal. So this is assuming now that we're doing an axial scan and we're doing the slice selection in the Z plane. So we also need to determine how we're going to get spatial information in the XY plane. So in the X direction, we can apply a spatially dependent precessional frequency gradient to the protons. And in the Y direction, we're going to apply a spatially dependent phase gradient, or GY, to the protons. Okay, so how are we going to do this frequency encoding in the X direction? So during the data acquisition, we're going to apply a magnetic gradient, GX, to make the nuclei precess at slightly different frequencies. So this is similar to what we did in the Z direction, okay? So here's a 3x3 example. The highest negative gradient on the left side, the highest positive gradient on the right side, and because of this, we can measure the spatial locations as we go along in the X direction. phase encoding, we're going to call the Y direction for our phase encoding in this example. And what we're going to do is we're going to resolve spatial features by using the phase information of the proton spins. And we're going to apply this before data acquisition. So here's a 3x3 example. And before we apply the Y gradient and after we apply the Y gradient. So after we apply the Y gradient, they're going to be at each a slightly different phase, and we're going to use this to distinguish the tissue in the Y direction. Okay, so here's an example of spatial encoding gradients. And what you see on the right here is called a pulse sequence diagram. So this is going to show you how we're going to collect our image, okay? So the first thing we're going to do is we're going to do our 90-degree, well, we're going to apply our Z gradient so we can select our slice, okay? And then once we do that, we're going to apply our RF pulse. Then we're going to do our phase encoding. That goes on right before we collect the signal. And then as we collect a signal, we're going to apply our frequency gradient. And you can see about down here at the bottom, we're collecting our data points while we're applying this gradient. And because of all these things that we've done now, we can spatially determine where we're collecting the signal from in our data. Okay, so let's look at some other pulse sequences with these same type of diagrams. Are you guys all following okay? I know it's a little complicated and I'm really just skimming over the surface here. Okay, so here's our spin echo gradient, okay? This is our refocusing of the dephasing. So again, it's used to refocus the T2 star effects from the inhomogeneous field so we can obtain a true T2 image. So in terms of this pulse sequence again, okay, so this TR at the top is the time between when we apply our RF pulses. And this time TE is the time that we're going to use between when we send our signal and when we listen to it. So in the case of a spin echo, this is always going to be, we're always going to listen to our signal. You can see at the bottom here, the A to D, at exactly another distance between the 90 and the 180. Okay, so we're going to apply the 90-degree pulse. Then we're going to apply the 180, and then we're going to wait that same exact amount of time between when we applied the 90 and the 180 to listen, because that's the time that our signal is going to converge. So what we're going to do here is we're going to turn on our slice selection. We're going to put on the, we're going to send the RF pulse. We're going to do our phase encoding, and we're going to apply the pulse, the 180-degree pulse. Then we're going to wait, and we're going to turn on our frequency encoding as we read the data so we can get the spatial location of this. And the reason why you would keep applying a TR is because you want to collect the whole image. So you have to keep flipping as you go along through the data. If you just flipped it once, then you would only get a very limited amount of data. So we're going to flip everything. We're going to collect for a single slice. Then we're going to do another flip and go to another slice. Okay, so spin echo has high signal to noise ratio, which means we're going to get a lot of signal and just a little bit of noise, and it's because of this wonderful refocusing that we're doing of the pulse. The problem is that it takes a long time to collect. So say we have a TR of 2 seconds, and the number of, let's see, MP, I can't think of what it is right now. The number of pulses that we need to collect our whole data set is 256. Okay, so that would be the number of excitations or proton flips times the number of pulse sequences that we need, and times 2 seconds, because that's how often we're going to flip our protons. So this is a single slice, I'm sorry. Back here, we can, now I'm confusing myself, I'm sorry. This is for doing, this can be also done for a multiple slice tissue. Okay, so we'll keep flipping, and okay, so we're only actually collecting one line in the phase direction when we're doing this, because you can see we're only turning on our frequency to do a section of the tissue. Okay, you're gonna have to trust me on this. So anyways, so if we times all these out, we see that we get 8.53 minutes, and this is the time that's needed to collect one slice, okay, for a spin echo here. And so while we can have a really nice high quality signal with this, it's going to take us a long time to collect somebody's whole brain. In fact, this is too long for functional MRI, because we want to see the changes in the blood flow, and if we have to wait 8 minutes, then these changes will be done, gone, and moved on to something else by the time we can collect the data. So one thing that we can do is use this gradient echo pulse sequence. So this does not apply the 180-degree refocusing pulse, but it allows us to collect data faster. So instead of measuring the signal at the peak of the rephasing, we're just going to measure the echo of the decay signal. So since T2 star decay is faster than our actual T2 decay, we can have TE and TR be shorter. Another thing we can do to make this faster is, instead of flipping all our protons exactly 90 degrees every time, we can flip them a shorter amount, so that it takes a shorter amount of time for the T1s and the T2s to happen. So we're doing all of this to try to increase our speed of collection. Now, this won't give us a nice, beautiful, high quality signal like before, but it's going to increase the speed of collection for us. So here's an example of it. So we turn on our slice selection, do a pulse, then we apply our phase and frequency encoding, and we listen to our echo time a short time after. So then we can just keep doing this over and over again, and it's a faster way to collect the data than doing the spin echo pulse sequence. Okay, so when we get to echoplanar imaging, this is something that we use for fMRI. And when we're doing this, we collect a single slice of data all at once. Okay, so you can see the trajectory here that we're going to use to go through the slice of data. So what we're going to do is we're going to collect each line. We're going to turn the corner and go backwards and collect, and keep doing that through the image. And we're doing that instead of going one line, going back to the beginning and the next line, because it's much easier to turn our gradients to follow this trajectory through the whole slice than it is to make it go all the way back to the beginning. So we can collect very rapidly using this technique. Again, it's used to collect an entire slice in a single echo. So we're only using one flip, and then we're collecting the whole slice. And we can collect the slice in about 100 milliseconds using echoplanar imaging, which now we're on track for fMRI, because we're collecting fast enough to see these changes in blood flow. So I like to think of the X and Y gradients sort of like a labyrinth game. Have you guys ever played this game where you put the ball on the track and you have to turn the X and the Y? I guess everybody doesn't think in terms of X and Y. But in order to keep the ball moving through this maze, you have to turn X and you have to turn Y, and you have to turn them right at the same times in order to keep this on track. So I kind of think of the gradients like this. We're moving this way, then we have to move this way, then back this way, and all instead of the location here now, we're looking at magnetic fields. Okay, there's another quick imaging technique called spiral imaging. And when I first started using fMRI, we use this technique a lot, and we don't use it so much anymore. I'm not quite sure why. Everybody seems to have gone more towards the echoplanar image, but this is non-rectangular, so it even allows us to be faster than those rectangular gradients where it has to turn the corner. Because in this case, it doesn't have to turn any corners. It just reads out like this. So you again collect a whole slice with one RF flip, but again, now you're collecting in a circular manner. And there's some benefits of using this because you can do things like oversample the middle and do less sampling on the outside. And you're going to see later when we start talking about K-space, how this might be an advantage because we're oversampling some of the lower frequencies that live near the axis versus the higher frequencies. Okay, so we're going to talk about how we record the signal now, our free induction decay signal. Okay, so first of all, our voltage-induced FID signal or free induction decay has to be amplified. So we take this pre-amplified signal and we're going to demodulate it. So it has a very high frequency, and it's difficult to digitize at this frequency, so we're going to demodulate it to a lower frequency before we collect it. Okay, then we have this quadrature mixer. It splits the signal into two equal magnitude components. It mixes the real sine signal and the imaginary signal with the cosines and sines. So you'll see, remember I told you our signal was an oscillating signal. So we can use frequency information to record this signal. Actually, it is frequency information when we're recording it. We're gonna low pass filter to get rid of any of the really high frequency noise. We're gonna then amplify the signal, and then we're gonna digitize the signal. This isn't really my area of expertise, but I just wanted to show you guys this so you had an idea of what was done to the signal as we collect it. Okay, so the free induction decay signal is a measure of the frequencies that are coming from our atoms, right, as we manipulate them with the MRI machine. And this frequency space is referred to as K-space. Again, the X direction represents information from frequency encoding because those were our frequency gradients, applied gradients. The Y direction represents information from phase encoding because we turned on our phase gradients for that. And the space between these points that we collect is set by what we define as our field of view. So our field of view is going to be related to how closely we collect these samples in K-space. Okay, so again, here's the pulse sequence, and here's how we might collect these. K-space is a frequency space for two-dimensional spatial frequencies. And if you remember when we were talking about frequencies yesterday, we said we can use the Fourier transform to go back and forth between a time domain and a frequency domain. So now we're going to use the same Fourier transform, but we're going to use it spatially to go back and forth between a two-dimensional frequency space and what we're going to call our image space. So the images that we collect don't actually look like a brain at all. They look like a splotch on a piece of paper or on the computer. So you can see here on the left what our signal might look like in K-space. That's again the frequency space that we're collecting our data in. So in order to get this image, we have to do a two-dimensional spatial Fourier transform. So once we do that, then we get the brain picture on the right, or the piece of tissue, or whatever we're looking at. So just a little bit of information about K-space. The center of K-space represents the lowest frequencies. So this contains the bulk of our image information. And as you increase from the center, you start getting higher frequencies. These higher frequencies contain more of the details of the image. We're going to see this a little bit. So again, we have these two-dimensional spatial frequencies, and we're going to have an imaginary and a real dimension here. I believe the real dimension is going to be the frequency, and the imaginary is going to be the phase direction. So each data point is actually a complex number with real and imaginary components, which isn't going to make a whole lot of sense to us until we do the Fourier transform. And here's what this two-dimensional Fourier transform looks like. It's a pretty complicated equation, so we don't do this ourselves. We let the computer do it and spit out the image. Now, in the early days, when we used to collect this, we would actually get our data in the frequency space. So we would take our raw data. First thing that we would do to it, in most cases, would be do this two-dimensional Fourier transform to get the image. Nowadays, the scanners that they make typically just do this automatically when it's in real time as it collects the data. So you can actually get the brain and see it on the screen. Even as fast as our functional data comes up, we can see this in real time as we're collecting it. So it's easy to forget that we're actually collecting in this frequency space. So I just want to show you what two-dimensional spatial decomposition into these signal components would look like. So here's our K-space, and if we look at it from one dimension, we can get something like this 1D Fourier projection. And this is what we use when we decompose a time signal into sines and cosines. So if you see there the yellow signal, it's equal to the sum of different sines and cosines at different frequencies and at different amplitudes on the axis. While we can also break our image space down into this as well. And you see the brain image there, and you can start to see how we might decompose this into other parts, into sines and cosines. But actually what we're going to see on that image is stripes, okay? So it's going to look like stripes on this image. So if we take this brain here and we can decompose it into stripes that vary at different speeds, then we can start to see the signal. So how is K-space related to image space? Well, it's based on these two-dimensional blocks of stripes, okay? I think I have some more examples. Do you guys kind of understand? So the slower you do your stripes, the lower frequencies are going to contain the bulk of the information. But when you start doing really quick stripes, then you can start to get the detail or the higher detail in the picture. This kind of shows how low and high frequencies relate to an image. So the image in the middle is our whole image. You can see it's an image of an airplane. Can you guys see that okay? Okay, so on the left side there, what we've done is we've cut out the high frequency information. So you can still see the bulk of the image, the airplane there, but the high frequency or the fine details that would be those faster stripes are missing from this image. So you get kind of a blurry picture, but you sort of get the idea of what the picture is. Now on the far right here, we've removed the low frequencies. And what you get, then you can see it sort of looks like an outline of the plane. This is the higher resolution detail of the image. And when you combine these together, of course, you get the middle image, which contains both the low frequencies and the high frequencies. This just shows how a pulse sequence diagram that we've been looking at, again showing when we do our flips and when we do our readings, might be related to the K-space of the image. Okay, so let's look at EPI again. When we're doing an EPI image, we are actually collecting all of K-space at once. We're not distinguishing collecting low or high frequencies. We're just going through and we're collecting all of it, low, high, and high frequencies equally. But again, like I told you before, if we're doing a spiral image, we can adjust how much we want to collect of this. We can do a tighter loop in the middle and get more low frequencies, oversample the lower frequencies, or we could do a tighter loop at the higher frequencies and oversample the higher frequencies. So it depends on how dense we want to make the spiral in the different locations at what frequencies we'll get. Okay, so now we're going to talk a little bit about the instrumentation. And as I mentioned before, there are three main components: the main magnet, the three magnetic field gradients that are going to use to distinguish our spatial information, and we have our RF coil. Okay. The magnetic field should be strong and as homogeneous as possible. And again, the center is called the bore, and that's where the person lies. There are three types: a permanent magnet, which is made out of a magnetic material. For example, you would get a piece of cobalt and make a magnet out of that, but it's very heavy. Okay, resistive magnets are created by the passage of a constant current through a conductor. For example, through a piece of copper, and you could make this magnetic. But what we tend to use in our high field strengths, those are field strengths over 0.35 Tesla, are these superconducting magnets. And using these superconducting magnets, we can get a really high field strength. So a superconducting magnet we can create by reducing or eliminating resistance in a conductive material. So these wires are typically made of a special alloy, and they are kept at a very low temperature. So we're talking like 9 Kelvin, which is pretty close to absolute zero. And to get to this low temperature, we achieve this by surrounding a layer of liquid helium. We have a layer of liquid helium, then we surround it by a layer of liquid nitrogen. And by keeping it at this very low temperature, we can put a current in our wire, and at this low temperature, we have very little resistance in the wire, so we can just put a single current in there, and this current will keep going around and around. And remember, electric and magnetic fields travel together, so by doing so, we can keep this constant magnetic field in place. The one problem with this that I mentioned before is that this leads to a permanent magnetic field. So we can't turn this magnetic field on and off. We can't turn it off for the night when we leave. The only way you can get this magnet to turn off is to let all the coolant out and bring the temperature of the wire up, and then the magnetic field will go away. People do this in emergency situations. It's called quenching the magnet. It's when you get rid of those gases and the temperature goes up and the magnetic field goes away. It's a very expensive thing to do to quench the magnet. And interestingly, we've had some incidents where the magnet just self-quenches, and I'm not quite sure. It's actually happened a few times this year at the MR Center, and nobody's very happy when they come in the next morning and the magnet has quenched in the night. Okay, the spatial gradient coils are, again, to encode the spatial informations, is the gradients of about 4 Gauss per centimeters, and therefore we can use copper and cooled with chilled water. These must be switched on and off very rapidly during data collection, so we can adjust our magnetic fields to measure. And this is what limits our rate of how quickly we can collect the data, how fast we can switch these magnets on and off. And again, these are the loud knocking noises that you hear when you're getting an MRI, are these gradient coils switching around and the magnetic field adjusting within these. And it's interesting, but depending on what pulse sequence you use, or depending on the sounds that you're going to hear with the gradient switching. Okay, so this just shows a bit about the gradient coil configuration, the X, the Y, and the Z gradient coils to control, again, our spatial information as we measure these. Okay, the RF coil. The RF coil is pretty important for sending the pulses to flip our protons and for detecting the signal. So this is called a transceiver. And you can see at the top here how close this RF coil is to a person's head when you put them in the magnet. It's this little box area, and it actually snaps onto the to the table when we put a person in there. And this is a kid, so he's not too uncomfortable in there. But if you get a really big guy in there, sometimes their nose is only maybe in a few millimeters even from the coil. And that can be pretty intense and intimidating, especially if it has to be on there for a long time. And when we used to scan these big men who were potentially violent offenders, even these big men sometimes had trouble with these things being so close to their face. I'm a little on the claustrophobic side myself, so I can certainly understand. So they have different geometries to image different parts of the body, but if say you're going to image somebody's brain, you would put the RF coil right over their head. Say you're going to image somebody's knee, you would put the RF coil over their knee. So the coil is very important to be around what part of tissue that you're going to scan in the body. Okay, so one thing that we need to do is we need to shield the magnetic field. The magnetic field is very large, and again, with the superconducting magnets, the field is always on. It's so strong that it can affect things that are nearby, like computers, other equipment, making safety issues. No pacemakers are allowed. So what is done is the room that the magnet is in is called shielding, and it's generally surrounded with copper or nickel. And so if you look at this picture on the bottom here, this is what the control room looks like at our center, and you can see that this distorted image here of the magnet inside the next room, and that's because of these copper and nickel things that are surrounding this room to try to contain the magnetic field. So when we talk about safety, we're going to talk a little bit more about this, but we do have safety lines around the rooms that represent how much the magnetic field drops as you get away from the magnet. Okay, so we're going to talk now about contrast agents. Now, we don't typically use contrast agents in MRI, but you may want to use them in special cases. Say you're trying to look at a tumor or something that you really want to mark better than what you can get with our tissue contrast characteristics. Okay, so we usually have enough contrast with T1 and T2 weighting, but sometimes contrast agents, again, are used when they're looking for very small or special cases of pathology. There's two types of contrast agents, paramagnetic and superparamagnetic. So metal ions with large number of unpaired electrons can be used as a paramagnetic agent. Again, paramagnetic things are that develop a magnetic property when you place them inside a magnetic field. So they're not magnetic until you place them into the field. Gadolinium is what is typically used. And interestingly, our safety officer, who I work with at the MR Center, she keeps up with these things, but she had seen some things recently in the news about long-term bad effects of having gadolinium. So they may start thinking about using this contrast as freely as they do when they do these images. So these metals are toxic, and these agents shorten the T1 and T2 of protons attached to neighboring water molecules. And they're mostly used to detect brain disorders. So here's an example of gadolinium contrast. Here's a metastatic deposit involving the right frontal bone. And this is, the left is before contrast, and the right is after they've applied the gadolinium contrast. So you can see, they can see more details of what's going on in that tumor after they put that contrast in there. We don't use contrast agents at all for functional MRI. These superparamagnetic agents are small magnetic particles. They can be 30 nanometers or less in diameter, and they actually contain iron. And when you inject them into a patient, they can cause inhomogeneities in the magnetic field. So they're negative contrast agents, so they cause a reduction in tissue intensity when they accumulate. And this, okay, so the arrows on this MRI are showing a dog's heart and where there are stem cells located. So one thing that's really cool that they can do with these is have these iron nanomolecules and label stem cells with these and then inject stem cells. So as these stem cells turn into different types of cells for different types of treatment, they can act, these nano molecules of iron actually stay in them, so they can track over time and see what's happening to these cells as they become different types of cells and are used to treat different illnesses and things. I know you guys, I don't know how much you know about stem cells. I know just a wee little bit about them, but I think it's pretty cool that you can label them and track them over time. Very interesting. Okay, we're going to talk a little bit about image characteristics, signal to noise ratio, contrast to noise ratio, and sources of artifacts in our image. Artifacts, of course, being unwanted noise that we want to get rid of to get a better image. So the signal to noise ratio in an MRI image is always better at higher field strengths, which is why people are pushing for these 7 Tesla magnets and even higher. The signal to noise ratio is also dependent on the tissue type and the parameters that we're going to use. And the T2, TE, and TR are, of course, the parameters that we can select. T1 and T2 are, again, inherent to what type of tissue you're looking at. The sensitivity of the RF coil is also going to help determine how much noise is in the image. And of course, as we saw yesterday with the ERP data, you get better signal with more signal averaging. Another thing that's going to depend on is the field of view that we do and the number of encoding steps that we use. So the more densely we collect our data, and the more out into the higher frequencies that we collect our data, is the more detail that we're going to see in our image. And it's better when we increase our slice thickness as well. Okay, spatial resolution. The point spread function is dependent on the pulse sequence, and it's affected by the digital resolution. So, like I mentioned, the further the field of view in K-space, the better resolution. The more you collect out in the higher frequencies, the better detail you're going to get. The width of this sync function is inversely proportional to the number of phase and frequency encoding steps. And remember, I showed you those functions that are used to turn on and off the encoding gradients, and the degree of T2 star relaxation. So how much field inhomogeneity we have in the image is going to affect our spatial resolution as well. Okay, so this is just an example of how T2 star affects the sharpness of a line through an image. And basically the idea here is that the wider the point spread function, the more smooth our image is, the less sharp profiles we're going to get. This is, I'm not going to get into this too much, just a perfect image would be the one on the left. With T2 star affecting, we get a smaller point spread function. But if we do a convolution of these two things together, where our actual function is going to look like this on the right side. Another thing that's looked at is the contrast to noise ratio. Again, these are affected by the parameters of the tissue and the parameters that we set. T1 contrast is better at a lower field strength because we have a slower relaxation into the B0 plane. So the higher our magnetic field, the faster it's going to pull those atoms back into the field after we send our RF pulse. And things that also affect this are the same things that affect our signal to noise, like the field strength, RF coil sensitivity, how much we average, our field of view, etc. So there are people who sit and think about these things a lot to try to make better images all the time. Well, I'll just go through the artifacts and then we'll take another break. Is that okay? Okay. If you undersample the image, you could get aliasing. So if any of you have taken Fourier analysis, time frequency analysis, you understand what this aliasing is. So to tell you, say your signal is going slowly like this, but you're only sampling at a slow rate. Well, if you do that, you're not going to catch all these peaks and valleys. So that's called undersampling. So you're going to miss your frequencies because you're not sampling fast enough to catch all those ups and downs. So that would be called undersampling or aliasing, and those cause problems in if you're doing whether a one-dimensional or a two-dimensional Fourier transform. You could have ringing artifact, which is an effect of having sharp corners in your frequency field. You can have patient-related motion, what's called susceptibility artifacts, RF-related artifacts, and inhomogeneous magnetic fields, and gradient-related artifacts. Okay, so this is what an aliasing artifact might look like in a spatial domain. And it's called a wraparound error, or the object is outside the field of view. And what you can see here is that this is somebody's abdomen in their hand, but what happens in this case is the top of the hand actually comes out in the bottom of the image here. And this is due to problems with sampling and in the field of view. This usually happens in the phase encoding direction. The sampling rate is less than the range of frequencies in the free induction decay signal. So again, we're not sampling those frequencies fast enough. And to get rid of this type of error, you might want to increase your sampling rate. Okay, so this is a ringing artifact, and this also, if you know anything about time frequency analysis, you can see that. But what's actually happening here is that although we have these sharp corners, we cannot define those well with sines and cosines, right? Because our sines and cosine functions are smooth. So that basically is a problem of ringing artifact. And you can see here that this should be a homogeneous type of looking thing, but instead we get these stripes in the tissue because of it. And one way to get rid of this would be to try to fit it with higher frequency functions. Okay, patient motion is a big problem. The MRIs sometimes, as you saw before, they take a while to collect, and much more time than a CAT scan might take. And people sometimes have trouble staying still. So you can see these sort of ghosting lines around the head there. That's due to this person moving around. And if the heart beating and the person breathing actually also causes some of these artifacts, because when the heart beats, it's sort of jiggling the head around. And when the person breathes, they're doing also causing the head and the brain inside the head to move while they're doing that. This picture here on the left just shows what happens if you take a phantom, which is something filled with a liquid that we image that should be completely uniform and move it. So you can see how the motion creates artifacts in that. Susceptibility artifacts happen when you're trying to image two different tissue types within one voxel. So remember, each of our voxels have this uniform intensity within them. So what happens at the boundaries of the image when you have a one voxel, but it contains both air and brain tissue? Well, that's the problem that causes these susceptibility artifacts. And you can see it leads to a lot of blurring and sometimes black holes in the image, because we have nonlinear changes in the resonant frequency at these tissue boundaries. So the resonant frequency of our tissue has a different frequency of the air molecules. And it leads to these variations, especially at the boundaries of different types of tissues. Okay, so here's another example, a patient with permanent metal in their mouth. This causes susceptibility artifact from the metal. And what you can see here is that you actually get a big black hole there. Okay, so let's take a break, and then we'll talk really briefly about safety, because we're going to have another lecture on that and some other types of imaging. And then I have some different things to show you on some more fun things to try to answer some of the questions and looking at the different brain pages that I recommended yesterday. Okay, we'll get going, and we're gonna just. Okay, I think I did. Sorry, I think I took safety out of this because we're going to study safety in a full hour next week. So I'm going to talk a little bit more about different applications of MRI, and specifically spectroscopy and angiography. Angiography is the study of blood vessels rather than the other brain types of tissue. Okay, so NMR is basically spectroscopy, and MR, as you saw, comes from this field. So what someone might use spectroscopy for is to measure different chemical contents of a single piece of tissue. So this is what the chemists do with nuclear resonance. So basically it's used to measure the structure and chemical content of a substance in a tube. And you can also do this in the body by measuring the chemical content of a single piece of tissue. And you might get something that looks like this, and you can attribute different chemical properties to their different frequencies. Okay, so I just put this, I thought it was interesting, and somebody had asked, what is the difference between nuclear magnetic resonance and MRI? And they say that basically it is the same thing. The difference is the letter N versus the letter I. NMR stands for nuclear magnetic resonance. MRI stands for magnetic resonance imaging. So it's basically uses exactly the same techniques. So what you do, again, is you align all these nuclei in a magnetic field, and you send an RF pulse at the frequency of resonance of the nuclei of interest. So say you want to measure how much nitrogen, say, for example, is in a piece of tissue. You send that resonant pulse at the frequency of the nitrogen, and then you listen for it to come back, and you can characterize how much is in that piece of tissue. And you would have to use the Fourier transform again to get the spectral information. So you don't have any spatial information, you don't have any spatial gradients, just getting the chemical content of a piece of tissue. And interestingly enough, you can use these tissues also to do imaging. If you send a different RF pulse at a different frequency, for example, instead of the resonant frequency of hydrogen, you send the resonant frequency of something else like nitrogen, then you can actually measure a nitrogen image of the tissue rather than a hydrogen image. But with spectroscopy, again, we're not getting any spatial information. We're just getting chemical content. And you can only do this technique on elements with odd atomic masses or odd atomic numbers, because these are the only ones that possess a spin, and when you put them in the magnetic field, they possess these polarized properties. So, for example, if you were going to do on hydrogen in a piece of tissue, the number of peaks tells you the different number of environments the hydrogen atoms are in. So say we have a piece of tissue, we send this resonant frequency of hydrogen to it, and we can see where the hydrogen is distributed in different chemicals by looking at the spectrum there. Okay, so the major peaks that we look at in spectroscopy are from lipids and waters. Lipids are fats, and the measurement is in parts per million. So, as I mentioned, you can also use these different elements to measure different properties. So, at the top here is a regular hydrogen image of the heart beating, and at the bottom is a sodium image. So I know I'm flipping back and forth between spectroscopy and imaging other elements, but this would be if you were going to send an RF pulse at the frequency to flip only the nitrogen atoms, not the hydrogen atoms, so you can see how the different images might look if you would just image nitrogen instead of hydrogen. And people do this. They're not quite sure what it means, but they use this more frequently now to image different elements in tissue. Okay, so this might be a pulse sequence that you would use for spectroscopy. And you would, again, just get a single voxel there. So you might have an X, Y, and Z gradient. You wouldn't need to do the encoding of the planes. You would just need to focus on a small piece of tissue. Again, this shows more of if you want to start getting tissue information of these pulses, and you want to try to see spatially what the different chemical content is of the different places in the tissue, you could again start using these X and Y gradients to get spatial location of the slice. Okay, so to use the spectroscopy in tissue, you might study oncology with cancer, you might study the different content of tumors. You could look at liver diseases, neurology, brain development, to see how, if there's a rejection components in an organ transplant. You can look at metabolism, nutrition, and different types of things that you might want to use this spectroscopy for to measure a chemical content. And this just shows an example here of a tumor versus a healthy tissue and what kind of chemical content information you might get out of these. Okay, here is a mammogram, and so you could also do spectroscopy in breast tissue and try to, in this case, God bless you, looks at how the chemical content of a tumor is changing after treatment, and the content that they're interested in is this choline, CHO, and they see after 1 day, after 42 days, and 70 days of treatment, you can see that this chemical is decreasing in the sample. So that's maybe an application that you might use spectroscopy for. I'm assuming in this case that the choline levels are related to the tumor properties in the tissue. So they want to monitor if this treatment is actually working, and they're using this technique to see that. Okay, I'm going to talk briefly about angiography, and these are methods used to look at blood vessels, and it's just going to be very brief. So you can measure blood vessels with MRI without injecting contrast, and one way you can do that is you can flip the protons in a plane, and as these are flowing through the blood vessels, they're going to continue moving through the tissue. So they've been flipped, and as they're relaxing back in time, they are going through the vessels. So you can capitalize on this property to measure and see where the blood vessels are within a person. So I'm not going to go too much into this, but one technique that they can do to do this is use a time of flight method. And again, since you flipped things and since they're still flowing and they're still flipped, you can use this to measure the vessels. So let's see. Again, here's the protons coming in, and we can flip in that plane, and we can see how the distribution is as new protons are going in that aren't flipped, and flipped protons are going out. And so you get very nice looking images of the blood vessels this way. Okay, here is another example of using a phase contrast method to do, again, angiography techniques. I'm not going to get into too much of this, sorry, unless anybody's really interested. But I just want to point out how nice of images you can get with angiography by using this flip technique. And these are images of vessels here. And so typically before, to measure blood vessels, you had to inject some kind of a dye and then watch as they flow through the vessels. But by using these properties of the tissue and using the fact that you can flip different times and measure different times as the blood flows through the vessels, you can get these really nice images of vessels without doing these contrast injections. Okay, so that's all I have on MRI, and we have about a little more than a half hour left, right? Okay, so tomorrow we're going to start talking about functional MRI, which is using these MRI techniques to look at function rather than looking at structure. And again, we're going to look at how we can capitalize on this T2 star to measure these effects of blood flow in the vessels. So we have a little bit of self-directed study, and I might need a volume. So there's a couple different things we can do. Okay, so I went through some videos last night to try to look at some of the questions you asked, which was what's the differences between males and females. Here's a video on why you remember some things and not others. This is a longer one on trauma.
A recent article published in the Proceedings of the National Academy of Sciences suggests that male and female brains differ in very stereotypical ways. By looking at brain scans, researchers found that, quote, scans showed greater connectivity between the left and right sides of the brain in women, while the connections in men were mostly confined to individual hemispheres. The only region where men had more connections between the left and right sides of the brain was in the cerebellum, which plays a vital role in motor control. So essentially, the study is saying that men's brains are structured in such a way that they're better with perception and coordinated action. So in essence, it plays into our stereotypes of why men are better drivers and why they're chefs, and why they're hairstylists.
Sorry.
That's right, they can more easily perceive something and then use their motor functions and control it. If you look at functional studies, the left of the brain is more for logical thinking. The right of the brain is for more intuitive thinking. So if there's a task that involves doing both of those things, it would seem that women are hardwired to do those better. What are your initial thoughts? Do you buy it? Are we reinforcing stereotypes here?
Yeah, I mean, for sure. I mean, but it's kind of, in some ways, it's like, so what? It's a bit of a so what? I mean, we know that women and men think things differently. We look at things differently. Mm-hmm. Men are from Mars, women are from Venus, or whatever.
Well, not necessarily. Right? We're much more alike than we are different. When you look at our DNA or anything, there's 1% difference versus 99% the same. We're made of the same stuff, essentially. And I think oftentimes our differences are overstated. We're more similar than we are. But this particular study, I think, is fascinating in that it doesn't just look at the size of your brain or size of particular parts of your brain or static images of your brain.
Right.
What it's looking at is how brain traffic flows.
Right.
So that, to me, is incredibly fascinating. And then the other part that I thought was really interesting is that they came to see these differences develop more in the adolescent years. So they say something like that the female brains and male brains had very few differences up to the age of about 13, but these differences became more differentiated around age 14 to 17. So the implications here are that it's not necessarily that we're born this way, it's just that perhaps we might be socialized to be this way.
That is interesting.
Isn't that cool?
So that has a direct impact on brain functionality, and what you're talking about is the neurons between, and so the connectivity within the brain itself and within the brain cells itself.
Yes, and it's essentially the way that information travels from one place to another. So the study looked at almost 1,000 participants, and they used a diffusion tensor imaging technique, which essentially allows us to really dive into the brain and see how information flows.
Gotcha.
Yeah,
gotcha.
Very sophisticated study.
Right, of course. Interesting. And the proposition is the fact that this is actually conditioned, or something that's brought about by nurture rather than nature.
We don't know, but given that the differences, because it could be something that has to do with whether or how our environment is shaping us. And I think, you say, so what? Yeah, there's the gender differences between men and women, but I think the bigger so what here and why it matters is that it has huge implications for conditions like schizophrenia or bipolar disorder. We can potentially treat men and women differently given the differences here.
What she was saying is that we treat men and women equally when we look at problems or disorders of the brain, and if we have a better understanding of the differences, then we can tailor to the different gender in a better way. But when I was looking initially at this question, I saw things that said there's very little differences between a man and a woman brain. So this is one of the things that I found that I thought was interesting. So like she said, we're more similar than we are different. They don't treat them different. That's the thing. Yeah. When I worked in the School of Pharmacy, go ahead. Exactly. We are different. We are very different chemically on a hormonal level between male and female. So he was saying that they're not taking that into account. They're just looking at the connections in the brain without adding in these other variables that might have an influence on it. I was going to say, when I was working in the School of Pharmacy, one big area that people were researching was pharmaceutical treatments. Of course, you guys probably aren't into pharmaceuticals as much as the doctors are in the U.S., but if somebody has some kind of a problem, they give the same medicine, same dosage, mostly based on your weight, but they don't take into account your metabolism might be different from somebody else's, and all the different factors that are involved in breaking down different drugs within the body. So they were looking, a big area of research in the School of Pharmacy was trying to do tailored treatments to different people based on their actual physiology and what was happening in the body, rather than just treating everybody the same. Okay, do you want to look at, I have this memory video. Do you want to look at that? Let's see. Why do we remember some things and not remember other things?
How do you decide what to remember? I actually don't remember. I was hoping that you did. No? Well, that's some medulla oblong garbage.
Brain joke.
Hey folks, Matt Lieberman here for D News. Our brains are capable of storing enormous amounts of information, so why do we often feel like our brains prioritize the wrong things when it comes to long-term memory? Every Monday on D News, we answer your questions, and Yash Barty wants to know, why do I remember something that happened 4 years earlier, but I don't remember what I ate last night for dinner? Good question. Well, according to computational neuroscientist Paul King, our brains prioritize memory creation and storage based on what we subconsciously determine is useful for our long-term survival, to which I respond, okay, that's all fine and good, but why did my brain remember several names of Scooby-Doo episodes and nothing I learned in algebra? I can't imagine a situation where my life will be saved by name-checking Jeepers, It's the Creeper, or Go Away, Ghost Ship. Well, your brain has no way of knowing what types of information will be useful in the future, so it has a variety of criteria to determine what to hold on to. First, your brain is really great at noticing patterns. Repeated facts, sights, sounds, and experiences must all be examined to determine whether they're worth remembering or if they should fade from perception. In addition, your brain prioritizes moments or facts presented earlier as they dictate what's to come, and whatever happened most recently as it's often the most relevant to your current situation. That's why most presentations begin and end with a summary of key points. However, the element of surprise may be even more powerful than that. A shocking or unpredictable outcome greatly increases retention, which is why you remember more about last season of Game of Thrones than you do about where you left your keys. I mean, unless you left them in the fridge. That would be incredibly surprising unless you are a sitcom character, because I think that only happens in fake life. On top of that, the brain also holds on to memories and thoughts that offer a strong emotional impact. Moments of extreme joy, sadness, or anger, for example, will always be easier to recall than clinical or boring moments, even if they're valuable for your continued success at work or school. Finally, and perhaps most significantly, your brain pays very close attention to moments and decisions that lead to positive and negative outcomes. So Yash, maybe you can't recall what you ate last night for dinner because it was simply unremarkable. If it had been incredible or god-awful, that meal would have left a strong impression on you and would dictate your future behavior. Outside of those criteria, your brain decides what to hold on to through another method called consolidation. So what's consolidation? Let's say you just learned how to drive a car. Every time you access the memories associated with your driving skills, aka every time you get behind the wheel of a car, the neuronal connections to those specific memories get stronger, making them that much harder to forget. Sleep has been shown to be vital to the consolidation of memories. While sleeping, the brain processes subconsciously learned information into tangible knowledge for later use. So if you really want to hold on to your memories and skills, go get a good night's sleep. So now we want to hear from you. What's seemingly the most useless thing that you remember? Let us know down in the comments and keep those questions coming too. We might answer them in another video. And hey, if you want to see more of me, check out this video that I did for SourceFed about a new bionic eye that's going to change vision for the better. Optometrist Dr. Garth Webb unveiled the Ocumetrics Bionic Lens, an ocular implant that perfects vision, offering eyesight 3 times greater than 20/20. Thanks for watching, and be sure to subscribe to D News for new videos every day of the week.
Okay, so that was. Do you guys want to see what people comment on? The dumbest things they remember? The most useless thing I remember is that chinchillas have about 50 hairs per follicle. This makes the animal the most hairs per follicle out of any other creature. I suppose this would be useful to know if I ever buy a chinchilla, but I don't plan on it. Why can I watch a scene from any of my TV shows and tell you exactly what episode it's from and what the name of said episode is, but I can't remember any of the stuff I learned in math for even 10 minutes. Last year I forgot my birthday. I didn't notice until my mother sent me a text wishing me a happy birthday. Then I forgot my best friend's birthday. I felt like a jerk, I'm gonna say. This one says, that sounds like a personal problem. So some of these are interesting. You know the web. The exact time I got up when I was about 7 or 8. I got up during a thunderstorm because I was scared. So the most useless memory I have, the fact that I know who Iggy Azalea is. All right, so that's just some interesting things on memory. This video on trauma is a little bit longer. I don't know. It sort of tells you why you might not remember traumatic experiences. Can you guys understand a Scottish accent? Pardon? Oh yeah. I could do that. Let's see. Do you know how to turn on subtitles? Oh, there's a place to do it? Okay, let's see. Scottish accent here. Oh, hold on. Do you know where to turn on? Is it here? Just the closed captioning? Ah, great.
We need to take a statement so we can establish what happened on Saturday night.
What time did you get back to David's flat?
So they're going to refer to our bottom-up processes of the limbic system here as a reptilian brain. It's sort of indicating that it's a very primitive part of your brain. And they're going to refer to the cerebrum up here as the neocortex, which is just another name for it because it's the neo, meaning it's the newest part of our developmental system. So I just wanted to let you know that.
What time? I don't know.
Can you give us an estimate?
I don't remember.
Would your pals remember what time you left the club?
He seemed nice.
She didn't remember much, did she?
I know. And now we've got to waste more time on a daft lecture. We know how to deal with victims. We've had years of experience.
Well, some of us have had more years than others.
I'm in my prime, I'll have you know.
That'll be right.
Today's session is about trauma. The latest in brain science will help you in your work. I'll start with a tour of the parts of the human brain. The reptilian brain maintains basic bodily functions. The limbic system is also instinctive. It deals with fear and pleasure. For example, you pat a dog, it senses pleasure, and without thinking, wags its tail. The neocortex is the site of logic, imagination, planning, and control. It's more sophisticated, but because it's conscious, it's slower than the older parts of the brain. The amygdala is a key part of the limbic system. It has one job: to sense danger and set off the alarm. When it's a matter of survival, the primitive parts of the brain override the conscious part. There are three possible survival responses: fight, flight, or the one that people don't think of, freeze. When the alarm goes off, blood and oxygen are diverted to muscles, adrenaline floods the body, and all systems that are not crucial to survival are switched off. Normally, the job of the hippocampus is to file memories so you can retrieve them later, but in times of danger, it stops filing memories, which makes it harder to gather evidence later on. Instead, the hippocampus switches to pumping cortisol. What's useful about cortisol is it stops us feeling pain, so we can focus on survival. Can anyone give me an example?
A farming accident where a man carried his own arm for a mile without feeling any pain?
Yes, excellent example. It is an evolutionary safety mechanism which is fast and instinctive. In essence, it's our body's very clever way of protecting us. To recap, an example of the three parts of the brain working together. You're standing at a bar. Your reptilian brain is keeping your heart beating. You're enjoying the pleasure of a nice pint with your limbic system. You're using your neocortex to work out if there's time for another before the last train. What could happen to make the amygdala kick in? What if this happened? The way you'd respond would depend not on your logical brain, but on your instinctive brain. Being glassed in a bar would be a traumatic experience. Who can give me another example of an event that can cause trauma?
War?
Rape?
A car crash?
Good, yes. Trauma occurs when a person is overwhelmed by something beyond their control. The survival brain takes over the rational brain. It can lead to post-traumatic stress disorder, PTSD, with symptoms that last at least a month. Vicarious or secondary trauma is something you may experience if you deal with incidents such as rape or sudden death, or think of Lauterbur, Dunblane. You're not superheroes. Having a brain makes you all vulnerable to secondary trauma. It's important to understand that when trauma occurs again and again, it can become complex PTSD, such as in domestic abuse or child sexual abuse. The alarm system in the brain becomes jammed. Memories are stuck in the limbic system, so a trigger can set off the alarm. The trigger could be anything: a colour, a smell, a sound, a sensation. Now, the indicators of trauma. What should you be looking out for?
Depression. Crying a lot?
Yes, that's one response. And at the other end of the spectrum, total numbness.
Nightmares. Flashbacks.
Stress.
Good, yes. And they may feel sick. Also, shame, feelings of guilt, inability to enjoy sex, social isolation, triggers. People often feel overwhelmed by the symptoms of trauma. This can lead to using alcohol or other drugs to block out memories, or self-harm, or dissociation when a person's mind detaches from reality. Indicators can be specific to the type of trauma. Say, dental problems, when someone who was orally abused avoids going to the dentist. A victim of abuse might bond strongly to her abuser. This is known as traumatic bonding, or Stockholm syndrome. And jumbled up memory, when a person's normal recording of memories doesn't work. Can you recall any times you've seen that symptom?
What time? I don't know.
A traumatized person may not seem like her usual self, or may be hypervigilant, on edge, or being startled by everyday things. Everyone is different. You never know what impact trauma will have. Symptoms can change from day to day. So what does all this mean in practice, in your job? A traumatized person's brain is protecting them, but that normal human response of self-protection can get in the way of evidence gathering. The US military has developed new trauma-informed interviewing techniques that you can use to work around this. Research shows that if someone seems vacant, they could be distracted by their traumatic memories. Try to ground them by asking a simple, non-patronizing question such as, "Are you thirsty? Do you want a glass of water?" This can help bring them back to the here and now. Don't expect a logical, linear story. Ask, "What can you recall just now?" Find out what the victim physically felt or saw. Working this way, from the instinctive sensory parts towards the logical parts of the brain, you'll get more results. In conclusion, 4 things for you to take away. Trauma response is the brain in survival mode. Repeated abuse can make trauma symptoms worse. In response to trauma, people will behave in unexpected ways. Remember, trauma is a normal human response to abnormal events.
We know that you've gone through a really painful experience, but we need to take a statement to understand what happened on Saturday night.
Are you able to tell us anything that you remember about his flat? Anything at all?
A dog. Barking.
Are you able to remember any physical sensations or feelings that you had?
Cigarette smoke. I can smell it now.
What was going through your mind?
I couldn't understand it. I just couldn't move, or even scream.
To freeze is a perfectly normal response. So you start with the memories, you don't start at the beginning. You have to engage with feelings to get to the facts.
Makes sense. Check you, Professor, getting all sciencey on us.
Well, if it gets us usable evidence.
There's life in the old dog yet.
Oi.
So that was sort of a explanation based on the treatment approach too, so of trauma. But I like the explanation they gave about the brain and how you may not be recording memories as they should be, or your brain and memory systems may be involved in other things and not be able to process exactly what happened during a traumatic event. So I thought that was a good explanation of that one. So, should we stop for today? Do you guys want to?